Let's build a band. I mean that literally. By the end of this episode, we're going to start with a single atom, line up a whole row of them, and watch a sharp energy level smear out into a continuous band of allowed energies. That band is the reason some solids conduct electricity and some don't. And the whole thing is going to come out of one little picture I already can't stop thinking about. A tiny arrow that twists a bit each time you step from one atom to the next. George, is that a fair promise?
It's a fair promise, and it's a good one, because tight binding is the rare model that's as simple as it looks and still hands you the deep result. Everything you just said, the row of atoms, the arrow, the twist, those are the actual moving parts. And the payoff, the equation we're marching toward, is E of k equals E naught minus 2t cosine of Ka. 6 symbols. When you understand where every one of them comes from, you understand how a solid gets a band.
Okay, I want that equation to feel inevitable by the end, not memorized. So let's not start with it. Let's start with the electron sitting on one atom. What does that even mean, quantum mechanically?
Let's set the stage. Picture a row of atoms, evenly spaced, all identical. Sodium atoms in a wire, say, or in our world, a line of little laser-made wells holding cold atoms. Each atom is a place the electron can live, a little valley in the energy landscape, a site. We label them with an integer, n. Site n plus 1, site n minus 1, marching off in both directions.
So n is just an address, house number 7, house number 8.
Exactly an address. And now here's the first genuinely quantum move. We say there's a quantum state that means the electron is sitting at site n, and we write it as a ket n. That's our notation for definitely at address n, nowhere else. One of these for every site.
And these are the building blocks, the Lego bricks.
They're the building blocks, and they're a very special kind of building block called a basis. 2 properties make them a basis. First, they don't overlap. If the electron is definitely at site n, the amplitude for finding it definitely at site m, a different site, is 0. We write that as the inner product, bracket m, n, and it equals 1 when m and n are the same site, and 0 when they're different.
That 1 or 0 thing has a name, doesn't it?
It does. It's the Kronecker delta, delta sub mn. 1 on the diagonal, 0 off it. Physically, it's just saying the sites are distinct places. Being at 7 is not being at 8. The second property is that these sites are enough. Any state the electron can be in is some combination of them. And that word, combination, is where quantum mechanics earns its keep.
This is superposition. The electron doesn't have to pick a house.
It does not have to pick. The most general state is a sum over all sites. C sub n times ket n, added up over every n. The electron is partly here, partly there, partly everywhere, and the numbers C sub n tell you how much of each. We call C sub n the amplitude for site n.
Now, how much is doing some heavy lifting there, because these amplitudes aren't ordinary fractions, right? They're complex numbers.
They're complex numbers, and hold on to that, because it's the single most important thing in the whole episode. Each C sub n has a size and a direction, a magnitude and a phase. Think of it as a little arrow in a plane. The length of the arrow is how much the electron is at that site. The angle it points, the phase, is the part that feels like it shouldn't matter yet, and it turns out to matter enormously.
Let me pin down the length part first, because that's the one I have intuition for. If C sub n is an arrow, the probability of actually finding the electron at site n is...
It's the length of the arrow squared. The modulus of C sub n squared. Magnitude squared. If the arrow has length 1/2, the probability is 1/4. Born's rule, applied to a lattice. Amplitudes are what the theory tracks, but probabilities, the things you measure, are amplitudes squared.
And the electron has to be somewhere, so all those probabilities have to add up to 1.
That's normalization, and it's just accounting. Sum over all n of the modulus of c sub n squared equals 1. The total probability of finding the electron across all the sites is 100%, because it's a real electron, and it's in there somewhere. Every legitimate state obeys that.
Okay, so right now I have a snapshot, a set of arrows, one per site, lengths that square sum to 1, but it's a still photograph, nothing's happening. What makes the electron actually do anything?
Beautiful. That's exactly the gap. The snapshot has no physics in it yet, no energy, no motion. To bring it to life, we need the object that knows the energy of every configuration and drives the dynamics. We need the Hamiltonian.
The Hamiltonian. Let's build it piece by piece. What's the first thing it has to say?
The first thing it says is, it costs something to sit at a site. Every site has an on-site energy. Call it E0. It's the energy of the electron parked at one atom, ignoring all the others. In our clean model, every atom is identical, so E0 is the same at every site. In the language of the Hamiltonian, when H acts on ket n, one thing it does is give you back E0 times ket n.
So if that were the whole story, if H just handed back E0 times the site every time, the electron would be stuck. Each site is its own little island with energy E0, and nothing connects them.
Stuck, exactly. Isolated wells, no drama, and a very boring solid. The physics, the entire reason a band exists, is the second term. The electron can tunnel. Quantum mechanically, it can leak through the barrier between one atom and the next, and reappear next door. And we put that into the Hamiltonian with a number called the hopping amplitude, T.
The hop. This is the electron jumping from house 7 to house 8.
Jumping, or better, leaking. It's tunneling, not climbing over. And we write it like this. When H acts on ket n alongside the E0 piece, it also produces minus T times ket n plus 1 and minus T times ket n minus 1. So, H on ket n equals E0 times ket n, minus T times ket n plus 1, minus T times ket n minus 1.
Let me read that back as a sentence. Sitting at site n has cost E0, and the Hamiltonian also connects site n to its two neighbours, n plus 1 and n minus 1, with strength T. Why only the neighbours? Why can't it hop straight from 7 to 10?
In principle it can, and in a more elaborate model you'd include it. But tunnelling falls off ferociously with distance. The amplitude to leak 2 atoms over is tiny compared to 1 atom over, and 3 over is tinier still. So we keep only nearest neighbour hopping. It's the leading effect, and, wonderfully, it's already enough to produce the band. That's the tight in tight binding. The electron is bound tightly to the atoms, only barely leaking to the neighbours.
I have to ask about that minus sign in front of T. Why minus? Is that physics or convention?
A bit of both, and it's worth a beat. We take T itself to be a positive number, and we write the hopping term with an explicit minus sign, because for the usual atomic orbitals, letting the electron spread out to the neighbours lowers its energy. Spreading out is favourable, so the coupling comes in with a minus. The upshot you'll see shortly is that the smoothest state, the one where the electron spreads most gently, ends up at the bottom of the band. If we'd chosen the other sign, the band would just flip top to bottom. So, convention we commit to now, and will stay consistent, but with a real physical tilt behind it.
Give me the picture behind that tilt, though. Why does spreading out lower the energy? I'd rather feel the minus sign than just accept it.
Here's the picture, and hold on to it, because it comes back at the very end. When the electron's amplitude has the same sign on 2 neighbouring atoms, the 2 arrows aligned, the wave function piles up in the region between them, and for the usual atomic orbitals that shared, in between amplitude, is a lower energy arrangement. Chemists have a word for it: bonding. Now flip one sign so neighboring amplitudes point opposite ways. The wave function is forced to pass through zero somewhere between every pair of atoms, a node, and every node costs energy. That's antibonding. So a smooth in-phase spread is cheap, and a jagged, alternating spread is expensive, and that -T in front of the hop is exactly what encodes it. Keep those two words in your pocket, bonding and antibonding, because the bottom and the top of the band we're about to build are going to turn out to be precisely those two extremes.
Good. I'll hold you to consistent. Now, you keep describing H by how it acts on each site, but I've also heard the tight-binding Hamiltonian called a matrix. How do I get from these hopping rules to a matrix?
This is one of my favorite little reveals. A matrix is nothing but a table of how the Hamiltonian connects each site to each other site. The entry in row M, column N, is the number bracket M, H, M. How much does H link site N to site M? You compute it by feeding site N into H and reading off the overlap with site M, and from our hopping rule, only 3 of those overlaps survive. M equal to N, and M one step to either side. So let's just read them off. The diagonal entries, row N, column N, are E0, the on-site energy. The entries right next to the diagonal, site N and site N plus 1, are -T. And everything else, sites that aren't neighbours, is 0.
So the matrix has E0 marching down the diagonal, -T on the 2 stripes just above and just below, and zeros everywhere else. It's mostly empty.
Mostly empty, and it has a name for that shape: tridiagonal. 3 diagonals carry everything, the main one and its 2 neighbours, and the vast rest is 0. That sparseness is the matrix picture of only nearest neighbours talk. When we run these models on a computer, that tridiagonal structure is a gift. It's why you can handle enormous chains.
Let me picture one row of that table concretely. Say I'm standing on row 7, the equation for site 7. What do I actually see reading across it?
You see almost nothing, and that's the whole point. Way over at column 7, on the diagonal, sits E0. One step to the left, column 6, a -T. One step to the right, column 8, a -T. And across the entire rest of that row, 0, 0, 0, all the way out. Then row 8 is the exact same little pattern, just slid one column over. Row 9 slid one more. The whole matrix is that one stripe, -T, E0, -T, marching down the diagonal and nothing else. That repeating stripe, drawn as a table, is the tight binding chain.
Now, I want to poke at a property of this matrix, because you set it up to be symmetric, -T above the diagonal and -T below, matching. Is that a requirement, or did it just come out nice?
It's a requirement, and it's a deep one. The Hamiltonian has to be Hermitian. For a matrix, Hermitian means if you flip it across the diagonal and flip the sign of every imaginary part, that operation is called the Hermitian conjugate, or dagger. You get back exactly the same matrix, H equals H dagger. In our case, E0 is real and sits on the diagonal, and the hop from site N to N plus 1 equals the hop back from N plus 1 to N. So the matrix is symmetric and real, and it's Hermitian on the nose.
And why does the universe insist on that? What breaks if H isn't Hermitian?
2 things break, and they're the 2 things you can't live without. First, the energies. The allowed energies of the system are the eigenvalues of H, and there's a theorem. A Hermitian matrix has real eigenvalues. Energy had better be a real number. You don't measure an imaginary joule, so hermiticity is what guarantees real energies. Second, and this is the one people underrate, Hermeticity is what keeps probability from leaking away.
Let's slow down on that one because I think there's a classic confusion lurking here. Hermitian versus unitary. I hear both words and I mix them up. Are they the same thing?
They're not the same, and separating them cleanly is worth a full minute. Then we go straight back to hunting the energies. Here's the clean split. The Hamiltonian is Hermitian. That's a property of H itself, the energy operator. Time evolution is unitary. That's a property of the thing that pushes the state forward in time. And the bridge between them is the exponential. The operator that evolves the state from now to a time t later is e to the minus I ht over h bar.
So H is Hermitian, and the evolution you build out of it, e to the minus I ht over h bar, is unitary.
Precisely. And the because is the whole point. That evolution operator is unitary because H is Hermitian. Hermitian is the generator. Unitary is the motion it generates. Think of it like this. Hermitian is the property of the engine. Unitary is the property of the ride. And unitary means length preserving. It rotates the whole collection of amplitudes around without ever stretching or shrinking the total.
And the total, the thing that's preserved, is our normalization, the sum of the probabilities.
That's the punchline. Because the evolution is unitary, the sum over all sites of the modulus of c sub n squared stays pinned at 1 for all time. The electron sloshes from site to site. The individual arrows lengthen and shorten and spin, but the total probability never drifts from 1. Probability is conserved, and if H weren't Hermitian, that guarantee would evaporate. Probability could grow or leak away, and the electron could literally vanish from your accounting. So hermeticity isn't bookkeeping fussiness, it's what makes the electron stick around.
Okay, that lands. H is Hermitian, energies are real, probability is safe. Now let's actually find those energies. We want the states that have a definite energy. That's an eigenvalue problem.
It's the eigenvalue problem, and it's the mathematical center of the episode. A state of definite energy is one that H simply scales. H, acting on the state, gives E times the same state, where E is the energy, a plain number. H psi equals E psi. Those special states are called the energy eigenstates, and their E's are the allowed energies. Everything the electron can do is built out of these.
So I take my general state, the sum of C sub n times ket n, and demand that H just multiplies it by a number E. What does that turn into in terms of the amplitudes?
Let's turn the crank because it's short and it's gorgeous. We take H psi equals E psi, and we ask what it says site by site. The trick is to project onto one site, to look at the amplitude at a particular site, n. On the right-hand side, E psi at site n is just E times C sub n. On the left, we hit both sides with bra n. We take the inner product with site n and collect everything that lands there. And here's the subtlety worth slowing right down for, because it trips everyone. Our hopping rule says H sends site n outward to its neighbors. But the equation at site n asks the reverse question. Which sites send amplitude in to n? Site n is the right-hand neighbor of site n minus 1, and it's the left-hand neighbor of site n plus 1. Those two, and only those two, have a hop that lands on n.
Walk me through what lands on site. The Hamiltonian has the on-site piece and the 2 hops.
Right. 3 contributions arrive at site n. The on-site term gives E0 times C sub n, the amplitude that was already there, scaled by the on-site energy. Then the hopping reaches in from both sides. The electron can hop into site n from its left neighbor, site n minus 1, and from its right neighbor, site n plus 1, each with amplitude minus t. So from the left, you get minus t times C sub n minus 1, and from the right, minus t times C sub n plus 1.
So the whole equation at site n reads E0 times C sub n minus t times c sub n plus 1 minus t times c sub n minus 1, all equals E times c sub n.
That's it exactly. E naught c sub n minus t times the quantity c sub n plus 1 plus c sub n minus 1 equals E c sub n. One tidy equation. But here's the catch that makes it hard and interesting. There's one of these for every single site, and each one ties the amplitude at n to its neighbours at n plus 1 and n minus 1. They're all chained together, a coupled equation at every site, infinitely many of them.
That's the wall, isn't it? Infinitely many coupled equations. If I tried to solve them one at a time, I'd never stop. So there has to be a trick, and I have a feeling it's your twisting arrow.
It is the arrow, and the reason the arrow works is a symmetry you can see with your eyes. Look at the chain. Every site is identical to every other site. Same well, same neighbours, same E naught, same t. The physics has no preferred origin. If you slide the whole chain over by one site, nothing about the problem changes. That's translational symmetry. And there's a principle. When the setup has a symmetry, the special state's respected.
So a state that respects sliding by one site, what does its list of amplitudes look like?
Here's the leap. If sliding over by one site leaves the physics unchanged, then the amplitude at the next site can't be genuinely different from the amplitude at this site. It can only differ by a phase. And here's why it's only a phase, not a longer or shorter arrow. If the length grew by some factor at every step, then marching down an endless chain of identical sites, the amplitude would run away to infinity in one direction and die to nothing in the other. And nothing about one identical site versus the next could justify choosing a direction to blow up. Same site, same length, only the angle is free to move. Same length arrow, rotated by a fixed angle. Every step down the chain, the arrow keeps the same length and twists by the same fixed amount. That's the guess, the ansatz. And we write it as C sub n equals e to the ikna.
Let me decode e to the ikna slowly, because this is the keystone. There's an n in there, that's the site. There's an a, that's the spacing between atoms, the lattice constant. And there's this k. What is k in the arrow picture?
In the arrow picture, k is the twist per length. Here's the cleanest way to hold it. The combination Ka, k times the spacing, is the angle the arrow rotates each time you step to the next site. One step, twist by Ka. 2 steps, twist by 2Ka. At site n you've taken n steps, so the arrow has twisted by k times n times a. And that total twist, that angle, is exactly what e to the ikna encodes.
And this is where Euler's formula comes in, because e to the I something is a rotation.
This is where Euler carries the whole show. Euler's formula says e to the I theta equals cosine theta plus I sine theta. And the picture behind that equation is e to the I theta is a unit arrow, length 1, pointing at angle theta. As theta grows, the arrow sweeps around a circle like a clock hand. So e to the ikna is a unit arrow pointing at angle kna. Every site holds an arrow of the same length, 1, and as you walk down the chain from site to site, the arrow clicks around by ka each time. A row of clock hands, each one a little further around than the last.
Let me put a number on it so I can actually see it. Say the twist per step, Ka, is 30 degrees.
Perfect. Run it down the chain. Site 0, the arrow points due east, 0 degrees. Site 1, 30 degrees around. Site 2, 60. Site 3, 90, pointing straight up. Keep stepping, and by the 12th site, you've added 12 30s. 360 degrees, a full turn. So you're back pointing due east, and from there, the whole pattern repeats. That's a wave rolling across the lattice, 12 sites to one full cycle, built out of nothing but the same arrow reprinted at each site with a little more twist. Small Ka, a long, lazy roll spread over many sites. Big Ka, a tight, fast winding that repeats after just a few.
That's a gorgeous picture. A line of clocks all ticking to the same offset. Now, the moment of truth. We take that guess. C sub n equals e to the ikna, and we shove it into the coupled equation. What happens?
This is the payoff, and it's clean enough to do out loud. Our equation was E naught C sub n minus t times the quantity C sub n plus 1 plus C sub n minus 1 equals E C sub n. Now what's C sub n plus 1 in our guess? It's the arrow one step further along, so it's the arrow at site n times one extra twist. C sub n plus 1 equals e to the ika times C sub n. And C sub n minus 1 is one twist backward. E to the minus ika times C sub n.
So both neighbours are just my arrow at site n times a forward twist or a backward twist.
Exactly. And now watch C sub n factor out of everything. The left side becomes E naught times C sub n minus t times the quantity e to the ika plus e to the minus ika times C sub n. Every term has a C sub n. It cancels off both sides, and what's left is an equation with no n in it at all. E naught minus t times e to the ika plus e to the minus ika equals e.
Wait, the fact that n cancelled, that's not a lucky accident, is it? That's the whole reason the guess was right.
You just put your finger on the deepest point in the episode. The n cancelling is the statement that our guess really is an energy eigenstate. Remember what an eigenstate needs. H scales the state by a single number e, the same number everywhere. If n had survived, the energy would be different at different sites, which is nonsense. It wouldn't be a state of definite energy. The n cancelling is the ansatz passing its own test. The twisting arrow is exactly the shape that translational symmetry demanded, and that shape is exactly what makes H act as simple multiplication.
So let me finish the arithmetic. E naught minus t times e to the ika plus e to the minus ika. That combination in the middle, a forward twist plus a backward twist, that simplifies because of Euler again.
Beautifully. E to the ika is a unit arrow at angle plus ka. E to the minus ika is a unit arrow at angle minus ka. Add them. One tilted up by ka, one tilted down by ka, and the up-down parts, the imaginary parts, cancel, and you're left with twice the horizontal part. The horizontal part is the cosine, so e to the ika plus e to the minus ika equals 2 cosine of ka. Pure real number.
And so the energy is
E of k equals E naught minus 2t cosine of ka. There it is, the equation I promised you at the top, and now every symbol has a home. E naught, the on-site energy, the middle of the band. 2t, twice the hopping. Cosine of ka, the twist per step running through a cosine. Feed in a twist k, get out an energy. That's the dispersion relation. It earns the name by being the rule that ties a wave's twist to its energy. And once you have it in hand, it's the entire personality of the band. Every question we ask for the rest of this series is really a question about the shape of this one curve.
I want to sit with the shape of that for a second, because a cosine has a very specific personality. It runs between +1 and -1. So minus 2t cosine of Ka runs between
minus 2t and plus 2t. When the twist k is 0, cosine of 0 is 1, the energy is E naught minus 2t. That's the lowest energy, the bottom of the band. When the twist is at its most extreme, we'll pin down exactly where in a moment, it's when Ka equals pi, cosine of pi is -1, the energy is E0 plus 2t, the top of the band, and everything in between fills in smoothly.
So the single sharp level at E0, the energy the electron would have sitting on one isolated atom, has spread into a whole continuous range from E0 minus 2t up to E0 plus 2t.
It has spread into a band, and the width of that band, top minus bottom, is E0 plus 2t minus the quantity E0 minus 2t. The E0s cancel, which is 4t. The bandwidth is 4t. That is the number I'd tattoo on this episode. Turn up the hopping. Let the electron leak between atoms more easily, and the band gets wider. Turn the hopping off, T goes to 0, the band collapses back to a single line at E0, the isolated atom. The band's very existence and its width is the hopping made visible.
That is the thing I wanted to feel inevitable, and it does now. A chain of identical wells plus a little tunneling equals a band of width 4t. And in the world you and I live in, the cold atom lattices, T is a knob.
It is a knob you turn with a laser. In an optical lattice, you make the wells out of interfering laser beams, and the depth of those wells sets how easily an atom tunnels to its neighbor. It sets there. Deeper wells, less tunneling, narrower band. Shallower wells, more tunneling, wider band. It's the same tight binding chain we just built, with a hopping you dial in real time. That's the machine underneath a lot of what we do. The black hole analog work runs on exactly this. A line of wells and a tunable hop.
Let's take a breath there and then turn to the other half of this, which is that mysterious K. We've been calling it twist per step, and that's a lovely geometric thing. But K clearly means more than that because it's now the label on our energy. Tell me the second life of K.
K leads a double life, and getting comfortable with both faces is most of what understanding bands means. Face 1, the one we built. K is a spatial frequency, a wave number. It measures how fast the arrow twists as you move along the chain. Twist per length. Big K, fast twisting, tightly wound. Small k, slow twisting, a long, lazy wave rolling across many atoms.
That's the geometric face. What's the second?
Face 2. K is the name of the state. Every value of k picks out one specific energy eigenstate, one particular pattern of arrows spread across the whole chain, and that state has energy E of k. So k is simultaneously a geometric quantity, the twist, and an address in a catalogue. Give me the state called K, and I'll tell you its energy from the dispersion. The site index N was the address in real space. Which atom? K is the address in the other space. Which wave?
And there's a piece of physics riding on K that has a name I definitely know from freshman quantum, momentum. You mentioned h-bar a moment ago.
We define the crystal momentum as P equals h bar k. And it looks exactly like the de Broglie relation from free particle quantum mechanics, where momentum is h bar times the wave number. For small twists, long, gentle waves, it behaves just like ordinary momentum, and that's a comforting limit we'll lean on. But I want to plant a flag and be careful here, because the word crystal in crystal momentum is a warning label.
Warn me. Why isn't it just momentum?
Because the lattice is allowed to give and take momentum in fixed chunks, it can absorb a kick from those evenly spaced atoms. So crystal momentum isn't conserved the way true momentum is in empty space. It's only conserved up to those lattice-sized chunks. H bar k is the right label for the state, and it acts like momentum in a lot of ways, but it is not the true free space momentum of the electron. Exactly how much slack there is and where those chunks come from is a part 2 conversation. For today, P equals h bar k, call it crystal momentum, and keep a little suspicion about the word.
Before I file that away, You said for small twists it behaves like an ordinary free particle. Can we actually watch the free particle fall out of the cosine? I'd believe it more if I saw where it hides.
We can, and it's a lovely little expansion. Take the dispersion. E of k equals E naught minus 2t cosine of Ka, and look right near the bottom of the band, small Ka. For a small angle, the cosine is approximately 1 minus 1/2 the angle squared. So cosine of Ka is about 1 minus 1/2 times Ka squared. Drop that in. Minus 2t times the quantity 1 minus 1/2 Ka squared gives minus 2t plus t times Ka squared. So near the bottom, E of k is about E naught minus 2t plus Ta squared times k squared.
So the energy climbs as k squared. That's a parabola.
A parabola in k. And that is exactly the shape of a free particle whose energy is p squared over 2m, a parabola in momentum. The bottom of our band is a free particle in disguise, which is the real reason h bar k acts like ordinary momentum down there. Small twists, long gentle waves, ordinary particle. And notice the steepness of that parabola is set by Ta squared. A big hopping makes a steep parabola, energy shooting up fast with k, and a small hopping makes a shallow, lazy one. That steepness is quietly handing you the electron's effective mass, and the link runs the way that surprises people the first time. A steeper parabola from stronger hopping means a lighter electron, a smaller effective mass, while a shallow parabola means a heavy, sluggish one. How heavy the electron acts when you push it is read straight off the curvature of this band, and that's the very first thing we chase in part 2.
Noted and filed. Now let's look at the shape of E of k more carefully, because you said the bottom is at k equals 0 and the top is at Ka equals pi. Is the dispersion symmetric? Does k and minus k give the same energy?
It's symmetric, and you can see it straight from the equation. E of k is E naught minus 2t cosine of Ka, and cosine is an even function. Cosine of a negative angle equals cosine of the positive angle. So E of minus k equals E of k. A wave twisting one way and a wave twisting the other way, same energy. That makes sense physically. Nothing about our chain prefers left over right. So a rightward wave and its mirror image leftward wave must cost the same.
And the band edges, top and bottom, is there something special about them, beyond just being the extremes?
There's something special that I'll only tease today, because it's the doorway to part 2. At the very bottom, k equals 0, and at the very top, Ka equals pi, the dispersion curve is flat. Its slope is momentarily 0, the way a hill is level right at the summit and right at the base of the valley. That slope, the rate the energy changes as you change k, turns out to be the speed the electron actually travels. Its group velocity. Flat slope, 0 speed. So the band edges are where the electron, in a sense, stands still. But group velocity, how fast a k-state moves, is a part 2 story. I just want you to notice the curve goes flat at both ends.
I'll notice it and want it. Okay, here's something that's been nagging me. We've now got 2 totally different ways to describe the electron. There's the site description, amplitudes C sub n, 1 per atom, how much are you at each address? And there's this new K description, which wave are you? How do those 2 live together?
They're 2 complete languages for the same electron, and the relationship between them is a genuine duality. My favorite structural fact in the subject. In the site basis, a state is a list of amplitudes over positions. Where are you? In the K basis, a state is a list of amplitudes over twists. Which waves are you made of? A perfectly localized electron, sitting at exactly one site, is, in the other language, a mix of every K, all the twists at once. And a single pure K, one definite twist, is, back in position language, spread absolutely evenly over every site.
So localized in one is spread out in the other. That's an uncertainty flavor.
It's exactly the position momentum trade in its lattice clothing. Pin down where the electron is, and you've smeared out which wave it is. Pin down which wave, one clean K, and you've smeared it across all of space. Position and twist are Fourier partners, two sides of one coin, and which language you reach for is just tactics. For hopping and locality, you think in sites. For energy and motion, you think in K. Same electron, same physics, two dialects.
Can you make that trade concrete? Give me one state that's dead simple in one language and a mess in the other.
Take the electron nailed to a single site, say site 0. In position language, that's the simplest thing imaginable. C0 is 1 and every other amplitude is 0. A single spike, one lit up atom, everything else dark. Now ask what twists that spike is built from. To pile up at exactly one site and cancel everywhere else, you need every K in the zone, all of them, mixed in with equal weight, a perfectly flat, even spread across all the twists. One sharp spike in position becomes a flat sheet in K. And it runs the other way just as hard. A single pure twist, one clean value of K, is a perfectly even spread across every site in position. The electrons smeared identically over the whole chain. Sharp in one language is maximally smeared in the other. That's the position twist trade with numbers you can actually hold.
All right, now I want to close a loophole. This whole time I've been letting K be any number I like. Twist per step, sure, dial it continuously, but a real crystal is finite. A real ring of atoms has some specific number of them. Does K stay continuous, or does the world clamp down on which twists are allowed?
The world clamps down, and the way it clamps is one of the most satisfying counting arguments in physics. To handle a finite chain cleanly, we do a standard trick. We bend the chain into a ring. Take n atoms and join the last one back to the first, so site n plus 1 is the same physical place as site 1. That's called a periodic boundary condition, and it spares us from fussing about the two loose ends of a finite wire while keeping the count exact.
A ring of n atoms. So if I walk all the way around, n steps, I have to come back to exactly where I started, same arrow.
Same arrow, and that consistency requirement is the whole constraint. Walk n sites around the ring, and the amplitude has to match up with itself. In our arrow language, going n steps means the arrow has twisted by n times Ka, and for it to come back to exactly where it started, that total twist has to be a whole number of full turns. A full turn is 2 pi, so n times Ka must equal 2 pi times some integer, call it m.
So the total twist around the ring is locked to whole turns. And if I solve nka equals 2 pi m for k,
you get k sub m equals 2 pi m over na, and that's the quantization of k. The twist can't be anything anymore. It has to be one of these evenly spaced values, indexed by the integer m. M equals 0 gives k equals 0, the no-twist state. M equals 1 gives the smallest non-zero twist, 2 pi over na. And so on up the ladder. The allowed k's are a discrete comb, spacing 2 pi over na between the teeth.
And there's a beautiful bookkeeping thing hiding here, isn't there? I started with n sites. How many distinct allowed k's do I actually get?
Exactly n. And that is not a coincidence, it's a conservation law for information. You started with n sites, n complex amplitudes, n addresses in position language. When you translate to the twist language, you must get exactly n distinct k states, n addresses in wave language. You can't create or destroy degrees of freedom by changing dialect. N sites, n k states. The two descriptions are the same size, which is what lets them be complete translations of each other.
That's the duality made into a head count. N in, n out. Now, you said there are n distinct k's, but I could keep cranking m upward forever. M equals 1,000, a million. Those give more and more values of k. How can there be only n if I can keep increasing m?
And that question walks us straight into the last big idea of the episode. Maybe the most beautiful one, the Brillouin zone. The resolution is that not all those k's are actually different states. Past a certain point, cranking k higher just relabels a state you already have. There's a redundancy, and once you see it, the only n of them clicks into place.
Redundancy. So, two different-looking k's can be the exact same physical state. Show me how that's possible, because on its face, a bigger twist sounds like a genuinely different wave.
Let's prove it with the arrows, in small steps, because this is the kind of thing that's magic if you rush it and obvious if you don't. Take a state with twist k. Its amplitudes are c sub n equals e to the I k n a. Arrow at site n pointing at angle k n a. Now consider a second state whose twist is bigger by one special amount, k plus 2 pi over a. I claim it's the same physical state. Let's just write down its amplitudes and compare site by site.
Okay, the new twist is k plus 2 pi over a. So the new amplitude at site n is e to the I times the quantity k plus 2 pi over a times na. Let me expand the exponent.
Expand it, that's the move. The exponent is I times k plus 2 pi over a times na. Distribute the na across the bracket. The first piece is I k na. That's just our original arrow. The second piece is I times 2 pi over a times na. And now look what happens to the a. In that second piece, the a in 2 pi over a cancels the a in na.
Oh, nice. The a's cancel. So the second piece of the exponent is I times 2 pi times n. I, 2 pi, n.
I times 2 pi times n. And what is e to the I 2 pi n? N is an integer. E to the I 2 pi is one full turn of the clock hand, all the way around, back to start, which is exactly 1. And e to the I 2 pi n is n full turns, still landing exactly on 1 for every integer n. So that entire second factor is 1 at every single site.
So the new amplitude at every site is the old amplitude times 1. They're identical. Every arrow, same length, same angle, site by site.
Identical at every site, which means it is the same physical state, not a lookalike, the same one. Adding 2 pi over a to the twist changes nothing you could ever measure, and that's the redundancy. K and k plus 2 pi over a are the same state, which means k is only meaningful within one window of width, 2 pi over a. Slide outside the window and you're just repeating states you already named.
And that window is the Brillouin zone.
That window is the first Brillouin zone. By convention, we center it on 0, so it runs from minus pi over a up to plus pi over a width of 2 pi over a, exactly one full period of the redundancy. Every physically distinct state of the electron has a k somewhere in that zone. All the twists that matter live in that one interval. Outside it, you're going in circles. Literally, you're going around the clock an extra time and calling it new.
And this closes the counting loop, doesn't it? Continuous window of allowed twists, width 2 pi over a, but the twists are quantized in steps of 2 pi over na from the ring condition.
Watch it close perfectly. The zone has width 2 pi over a. The allowed k's are spaced 2 pi over na apart. So how many fit in the zone? Divide the width by the spacing. 2 pi over a divided by 2 pi over na. The 2 pi's cancel, the a's cancel, and you get n. N allowed twists in the zone. N sites, n k-states, all sitting in one Brillouin zone. Every thread we've pulled ties off in that one number.
That is deeply satisfying. Let me make sure I can hold the whole chain of it. N atoms on a ring. The ring condition quantizes the twist into a comb spaced 2 pi over NA. The redundancy says only a window of width 2 pi over A is distinct, and the window holds exactly N teeth. N equals N. Nothing lost, nothing double counted.
You've got the architecture of the whole subject in one breath. And now, let me spend our last stretch on the two states at the ends of that zone, because they're the physical bookends of the band, and they'll set up everything in part 2. We already met the bottom, K equals 0, the center of the zone. What do the arrows look like there?
K equals 0 is no twist at all, so e to the I 0 NA. The angle is 0 at every site. Every arrow points the same way. All the clock hands, frozen, pointing the same direction.
Every arrow aligned, the smoothest possible state. The electrons spread evenly and in perfect phase across the whole chain. No wobble from site to site. That's the bottom of the band. Energy E, 0 minus 2T. It's smooth, it's gentle, it's the ground state of this band, and it costs the least. Now let's walk to the edge of the zone, K equals pi over A, and see the opposite extreme.
K equals pi over A. Let me build the arrow. The amplitude at site N is e to the I times pi over A times NA. The A cancels again. Pi over A times NA is pi times N, so it's e to the I pi N.
And e to the I pi is the deep one. The arrow rotated by half a turn, 180 degrees, which lands on -1. That's the famous identity, e to the I pi equals -1. So e to the I pi n is -1 raised to the n, which is +1 when n is even, -1 when n is odd.
So the amplitudes go +1, -1, +1, -1, marching down the chain. The arrow flips completely every single step.
Plus, minus, plus, minus. The staggered state, -1 to the n. Every atom is exactly out of phase with its neighbors. The arrow can't twist any faster than that. Flipping a full half turn per step is the most violent wobble a lattice of discrete atoms can even represent. Squeeze the twist any harder, and the redundancy just wraps you back into the zone. So this is the maximum meaningful twist, the shortest wave the lattice supports. Its wavelength is 2 atoms, one up and one down, and you've repeated.
And that maximally staggered state is the top of the band.
The very top, energy E 0 plus 2T. And there's a lovely symmetry in the two bookends. The bottom of the band is the electron in perfect harmony with itself. Every arrow aligned, the smoothest spread, energy lowered as much as the hopping allows. The top is the electron in perfect discord. Every arrow fighting its neighbor, energy raised as much as the hopping allows. Smooth costs the least, staggered costs the most, and the whole band of width 4T stretches between those two.
Let me try to say back the entire journey, because it actually hangs together as one story now. We started with an electron that could sit at any of a row of identical sites, described by complex amplitudes, whose squares are probabilities. We gave it a Hamiltonian, a cost E0 to sit, and a hopping T to leak to its neighbors, Hermitian, so energies are real and probability is safe. We asked for the states of definite energy, which gave a coupled equation at every site. Translational symmetry told us the eigenstates are twisting arrows, e to the ikna, and plugging that in, watching the site index cancel, handed us the dispersion, E of k equals E0 minus 2t cosine of Ka, a band of width 4t.
And then we understood the label on that band. K is a twist per step, and the name of a state at once. H bar k is its crystal momentum. With an asterisk we'll cash in later. Position and twist are two complete dialects for the same electron, the same size, n sites, n k-states. A finite ring quantizes the twist. The redundancy of k and k plus 2 pi over a confines the distinct states to one Brillouin zone, and the zone's two edges of the smooth ground state at the bottom and the staggered -1 to the n state at the top.
Which means we can build the band and name every state in it. But we can't yet make anything move.
That's exactly where we run out of road today, and it's the seam for part 2. We have the map of allowed states, but not the dynamics on top of it. So part 2 picks up 3 questions that all live in the shape of E of k. First, how fast does a given k-state actually travel? That's the group velocity, the slope of the dispersion we noticed going flat at the band edges. Second, how does an electron in the band respond to a push, an electric field? And the astonishing answer is that the curvature of E of k makes it behave as if it has a different mass, an effective mass, sometimes even a negative one. Third, what happens when you have real electrons, 2 per state, filling the band from the bottom? Because whether a band fills up completely or only part way is the entire difference between an insulator and a metal.
Group velocity, effective mass, and metals versus insulators. From the same curve we already have on the board.
All 3 fall out of E of k equals E0 minus 2t, cosine of Ka, and its slope and its curvature. We built the stage today, the sites, the hopping, the band, the zone. Next time, we let the electron loose on it and watch it move, respond, and decide whether its solid conducts. Same chain, same arrows. We just start asking what they do.
Then that's where we'll pick it up. Build the band today, set it in motion next time. Thanks everyone. Go find a row of anything and imagine the little arrows twisting down it.